So here's what I got for the your turn, the pi over 12. I used pi over 3 minus pi over 4. And so this works out to root 2 plus root 6 all over 4. I hope that makes sense for you. I'm going to go on to the next section here. It says, we can simplify expressions using identities. So for example 3, it says, consider the expression 1 minus cos 2 theta all over sine 2 theta. So this is the double angle identity section. So near the bottom, you'll notice that there is sine, here they're using alpha, it doesn't matter, sine 2 alpha equals 2 sine alpha times cos alpha. So there's one for the double sine identity. For cos, there's 3 different versions. And as you'll see, they're actually very closely related. So it says, consider that expression, determine the non-permissible values for this expression. Okay, non-permissible values, again, what we're going to do is look in the denominator. We're going to say, are there any examples where the denominator is equal to 0? So I'm going to think, okay, my non-permissible values happen when the sine of 2 theta is equal to 0. And I think it might be easier in this case if we substitute for a second here. And if I say, I'm going to let x equal 2 theta. So then if I rewrite this, I'm going to say the sine of x is equal to 0. When is the sine of x equal to 0? Let me think about that. Sine on my unit circle is simply the y value. The y value is equal to 0 here and in here. So I'm going to say for when x is equal to 0 or pi. So now when I'm thinking about my 2 theta, so then I could say 2 times theta, which I said was the same thing as x. The non-permissible values would be 0 and pi. Now my last step is to say, but I'm not interested about 2 theta. I want to know what theta, what angles for theta. So I would say theta would be equal to half of 0, which is still 0, and half of pi, which is pi over 2. And so those would be my 2 answers. Now when you think of it, like where is pi over 2? Pi over 2 is right here. So if I put that into my denominator, I would say, oh, when theta is pi over 2, well, twice pi over 2 is pi. The sine of pi is 0. So that's why it makes sense. So you got to think about when you're doing this double identity, what's being doubled is the angle, not the sine of the angle. Okay, the second one says, simplify the expression, the entire expression, not just the denominator, to one of the 3 primary trig functions. Okay, so I got 1 minus cos 2 theta and sine 2 theta. At this point, I think what we're going to have to do is substitute something from these formulas for sine 2 theta and also for cos 2 theta. Since sine 2 theta, there's only one option. Let's do that one first. Here, I'll find it. Okay, so in my denominator here, I'm going to say, instead of sine 2 theta, I'm going to do 2 times the sine of theta times the cos of theta. And where did I get that? Well, I got that from right here. Okay, so now for cos theta, I've got 3 options. I'm looking at them. I kind of like the second one and the third one better because it's only got, like in terms of trig functions, there's only a sine there. And for the third one, there's only a cos there. I'm going to pick this one here, and we're going to see how it turns out. So if you're doing this question on your own, you could plug one in. And if it doesn't work, you might try a different one. But let's take a look at it. So 1 minus 2 sine squared theta. So on the top, I'm going to say 1 minus, and then now I have to do the substitution here. So I'll put in parentheses, and that was 1 minus 2 sine squared theta. I'll make that a little bit bigger. Okay, so before we do any simplifying, I think we should remove the brackets and remember that there is a negative sign out front that needs to be distributed. So this would turn into 1 minus 1 plus 2 sine squared theta all over 2 sine theta times cos theta. Now my 1 minus 1 is going to simply turn into a 0. Now I have 2 sine squared theta over 2 sine theta cos theta, and I can divide both the top and the bottom by 2, and that cancels that out, and also by sine. So when I'm done all that, I'm going to get sine theta all over cos theta. What's my task here? To simplify to one of the three primary trig functions, which are sine, cos, and tan. That's the same thing as tan theta. And I'll put a box around it. Worked out great. Now let's say, just for the sake of argument, that you had picked a different one. Let's say that maybe you had picked, let's just go back over here. Maybe you'd picked this one, the cos squared theta minus sine squared theta. So I'll do this in green here. I would say, okay, looking back at this, I'll rewrite it from the beginning. I'll say, okay, now it's 1 minus, what was it again? It was cos squared theta minus sine squared theta all over. Now still, for the double sine identity, there's only one version. Okay, so then when I remove the parentheses from the numerator, it doesn't change too much. I get 1 minus cos squared theta plus sine squared theta all over 2 sine theta cos theta. Okay, so now this is a great question because it's going to get you ready for doing the trig identities, which is what we're coming up to. I'm going to recognize, hey, this 1 minus cos squared, I dropped my theta. I got to include my theta here. That 1 minus cos squared theta. Remember a long time ago, let me just see if I can find it somewhere. I think I'd said, like, hey, this is a really good one. Yeah, here it is. 1 minus cos squared theta is the same thing as 1 minus sine squared theta. And it all came from this identity over here. So I'm going to say, hey, I know that 1 minus cos squared theta is the same thing as sine squared theta. So in my next line, I'm going to write sine squared theta plus sine squared theta all over 2 sine theta times the cos of theta. And I think you might be able to see where we're going from here, because when I combine those two terms in the numerator, I'm going to get 2 sine squared theta all over 2 sine theta cos theta. And then that's the same place that we were over there after we canceled the 1 minus 1. So really, those three versions of cos 2 thetas, these three here, just are variations of a theme using that sine squared theta plus cos squared theta equals 1. And so if you pick the wrong one and you're good at doing what I just did here, 1 minus cos squared theta is equal to sine squared theta, you can still use any of them at any point in time. All right, let's take a look for example number 4. I can guarantee you 100% that you're going to find a question very similar to this, with numbers different, obviously, on a mastery check and a test, and on every single provincial exam that I've seen, there's been a question like this. So this is a really good one to pay attention to. It says if you're given cos alpha in, I wonder which quadrant that is, pi over 2, somewhere between pi over 2, and this is pi over 2 here, and pi. So it seems to me that that is quadrant number 2. And you're given cos beta, which is in, I think this is quadrant number 3, between pi and 3 pi over 2. Find cos alpha minus beta. Okay, so if I look up cos alpha minus beta in the formula sheet, and again, you don't have to memorize this, I believe it comes out looking like that. Now, we know what cos alpha is. We're given that one. Like, check, done. So I could substitute that part in. I could say, okay, I know that that one is equal to negative 4 over 5. I don't know what cos beta is yet, so I'm just going to sort of leave parentheses there for cos beta. I do know what cos beta, pardon me, it's right over here, negative 12 over 13. So I can draw that part in. So it's going to be multiplied by negative 12 over 13. And again, we're multiplying here, so I'll put these parentheses back. Plus, now I don't know what sine alpha, I'm going to put question marks here for a second because we're going to erase them and fill them in. We need to figure out what sine alpha and sine beta is. So it kind of reduces to a question that we did in chapter 4, but you may or may not remember, is if you're given cos, can you figure out the other things? So I'm going to just remind ourselves that cos, maybe I'll do a different color here, cos theta on the unit circle is just the x-axis, just the x value, but on any circle of any size, it's going to be x over the radius. And sine is going to be equal to the y over the radius. Tan, by the way, is y over x, but we don't need that right now. And how are these linked together? It's straight from Pythagoras. It's going to be x squared plus y squared equals r squared. So our task is use the information for both of those angles and figure out what the sine is. So for the first one, let's just think about the alpha first. So alpha, we have x equals -4. Y, we don't know yet. And r is equal to 5. Now let's just think, in which quadrant was that? That was in quadrant number 2. Something over here. So I know that my y value is going to end up being positive. I'll just put that up over there. Okay, so if I go, and you may even recognize this already, Pythagorean Triple of 3 squared plus 4 squared equals 5 squared. So you might already anticipate this y is going to be 3. But let's just go through the motions. We're going to say x squared plus y squared equals r squared. So I'm going to get -4 squared plus y squared equals 5 squared. So -4 squared is still positive 16 because the negative gets squared. So I get 16 plus y squared equals 25. 25 minus 16 is 9. So I'm going to get y is equal to the plus or minus of 9. Plus or minus of the square root of 9, which is 3. So, but which one is it? And because it's in quadrant 2, I know that my y value is going to be positive. So I'm going to say y equals plus 3. I'll put in parentheses maybe over here, quadrant 2 as a reminder. Okay, so what does that tell me? That y is 3 over here. So then I know then that the sine, and I'm talking not about alpha in this case, or about theta, I'm talking about alpha. Sine of alpha is going to be equal to, again, y over r. So the y is 3 over 5. So I can put that value, and I'm going to go put that in over here now. 3 over 5. And now we're going to try the same thing for beta. I think beta deserves its own color. What do you think? So, what color is this one? Oh, it's a neat little color. Okay, so here we have the cos of beta. I know that the cos of beta is equal to -12 over 13. And I believe that was in quadrant 3. So that was in quadrant 3, which goes down over here. In quadrant 3, the x value is negative, and so is the y value negative. So I'm thinking my x equals -12. My y, I don't know yet. My r is equal to 13. So you may know the 3 squared plus 4 squared equals 5 squared Pythagorean triple. So here's another triple that you get often. This is the 5, 12, 13. So let's try it out. X squared plus y squared equals r squared. So it's going to be -12 all squared plus y squared equals 13 squared. -12 is squared is 144. Plus y squared, 13 squared is 169. When I subtract 144 from both sides, I get 25. So y is going to be equal to the square root of 25 plus or minus, and it's going to be minus because of which quadrant it's in. So I'm going to say y equals -5, and I was going to say quadrant 3. That's why I know it's minus. So now I know that the sine of beta is going to be equal to y over r. So it's going to be equal to -5 over 13. And now I can go over here and write this in. -5 over 13. Okay, I didn't give myself too much room, so I'll just work this to the right. I need to multiply these two together. So I'm going to get 5 times 13 is equal to, what is that, 65? -4 times -12 is going to be equal to positive 48. Plus, and again, 5 and 13 is going to still give me that denominator of 65. 3 times 5 is -15. So 48 minus 15 is at 33. over 65 is my final. I'll put a box around it because I did so much work here. Okay, so that seems like a lot of work, but really it's kind of putting together things that we've done before. Is there another example? Yeah, there's one more example. Okay, so this is, you know what, this is a little bit of a long video, so I'm gonna pause now and I'll start another video so that it's a little bit chunked for you guys.